Hello, uh, my name is Jacob Martisevitz, and this is an exam prep session for the final exam of Dr. Goldsman's simulation class. Today we'll be going over the 2019 summer exam that he posted, and we'll be going through every single question, and I'll be answering it here on this sheet. Before I begin, I'm just going to briefly talk about some general tips and general information. So by this point, this is the third exam. The proctoring for this exam should be the same as the proctoring for the previous exams. All of the sort of logistics around the exam are the same as the previous exams, except this time you guys get up to 3 cheat sheets front and back. For the first exam, I believe you got 1 cheat sheet. For the second exam, you got 2 cheat sheets. And for this one, you get 3 cheat sheets front and back. I would recommend making full usage of those. And so definitely spend time putting those together. Another thing I'll point out is that this exam is cumulative, so everything in the course is fair game, and the material that will be covered, but with a heavier focus on the more recent material of this exam that happened in this course. So there's that. Other things I would sort of recommend is one way to know if you are in a good place for the exam is if you're able to solve all the questions on the practice exams, and then both this practice exam and the previous practice exams for exam 1 and 2, as well as being able to solve any of the homework questions. If you're able to do that just using your cheat sheet and sort of a calculator and pen and paper, as well as those chi-squared tables, the standard normal tables that are distributed with each exam. If you're able to do that, then you're in a pretty good place for the exam, I would say. So that's the rule of thumb I used anyway when I was a student and took this course. All right, so let's dive right into this exam, and starting with question 1. So question 1, true or false? You have basically you have 2 random variables, and you're told that the joint probability distribution f of x comma y is equal to cxy for 0 less than x less than 1 and 1 less than y less than 2. And c is some constant that makes this thing integrate to 1. So we want to just tell whether or not these are independent random variables. And the way that you can, so the way I would approach this is there's sort of like 2 checks that have to be satisfied for these to be independent. So two things for independence in these cases. So the first one is that the joint probability distribution should be able to be written as some function g of x and some function h of y. So you should be able to sort of break it up into these 2 pieces. And the second condition is that there are no funny limits. And what do I mean by funny limits? Well, like a funny limit example, this is a fancy way of saying that in the limits themselves, the values of x depend on the values of y. So a funny limits example would be, for example, 0 less than x less than y less than 1. So that this is like a funny limits example, because what the value of y is in those limits depends on the value of x. So in this case, we have our, if we actually start looking at this one, so f of x comma y is equal to c x, y, and we can split this up into if we split this piece and this piece, so this will be our g of x, and this will be our h of y, and so that basically meets the first condition for independence. And then we look at the limits, and we see that the limits for x do not really depend on y, and the limits for y also do not depend on x. So this condition has also been satisfied. And so in this case, this thing is in fact independent. These two random variables are independent, so the answer is true. And what's an example of like, something where they're not independent? Imagine example 1 is, let's say you had f of x comma y equal like 1 over x plus y. There's no good way of breaking this out because x and y are sort of in the fraction as the denominator. So this is one example that's not independent, where x and y are not independent. Another one is, imagine that, and I sort of already showed this, but the limits are sort of funny. So 0 less than x less than y less than 1. This would also not be independent if you had funny limits like that. All right, moving on to next question. Question 2. Show how to generate in Arena a discrete random variable x for which we have the probability of x. The x can take basically, basically just 3 different values. So x can be -3, it can be 3.5, or it can be 4. And the probability of each of those things, -3 will happen 0.3, or I guess -3 will happen with probability of 0.3, 3.5 will happen with probability 0.6, and 4 will happen with probability 0.1. And this 0, otherwise, this just says that for all other values, there's a probability of 0. And so this is really just more of an Arena question, and it's something, I believe a question like this was asked on one of the previous homeworks as well as maybe a previous exam. But basically, you just sort of need to be familiar with how Arena syntax works. And in our case, the way Arena syntax works is you, for these discrete random variables, you basically put it in CDF form. So you take the smallest one, which is so you basically put things in the form of like the like f of, I guess, x, and then the x value, and you just keep like putting like in these forms. So the first sort of value that we're interested in is -3, because that's the lowest one. So that means that this first sort of pair, the second thing is going to be -3. The first one is going to be 0.3 because that's sort of the probability that in the CDF that you're up to -3 so far. And then the next one, the next pair we have is 3.5 over here. And because we're doing the CDF, we take 0.6 and add it to 0.3 to get 0.9, because the probability that x is less than or equal to 3.5 is 0.9, and that's the definition of the CDF. And then finally, the last one, we have 4, and by this point, we have the CDF is at a value of 1, and so that's basically your answer. So it's 0.3, comma -3, 0.9, comma 3.5, and 1, comma 4, and that's answer choice B. So it's really just a matter of being familiar with Arena syntax and understanding how to go from this to a CDF. So, that's really what we're doing here. Cool. Question 3. True or false? In our Arena call center example, it was possible for entities to be left in the system when it shut down at 7 p.m., even though we stopped allowing customers to enter the system at 6 p.m. So in this question, this goes back to a lecture video that Dr. Goldsman recorded, and yes, basically I think he explicitly talks about this, where even though the last possible time that customers could enter the system is at 6 p.m., due to the nature of the simulation, and the chances that basically a callback could occur and the customers could sort of stay in the system longer, it's this is true. But more broadly, you can sort of imagine that in other sort of simulation settings, like, let's say that you have a store that stops letting customers in at 6 p.m. The existing customers might still be lingering around the store, for example, later. And so, even from that, if you look at it from that lens, like this would also be true. Like, most systems, depending on the behavior of the entities, can like have things happen in a long tail fashion and extend things later. Cool. Question 4. True or false? An entity can be scheduled to visit the same resource twice with different service time distributions on the 2 visits. And this is once again just an Arena question, and it is true. One thing I'll briefly say about Arena is I would probably recommend maybe rewatching the slides or either just rereading the slides or at least rewatching the lectures relating to Arena if you're feeling like a little bit unsure about some of the Arena stuff. Or what you can do is you can play the Arena lectures on like 1.5 speed or something else and just sort of like power through it, just to like really make sure. And another thing you can do is just review the past questions on the past exams, but if you really wanted to make sure that you're covered for anything, just rewatch the lectures one more time so the information is sort of fresh in your mind. Question 5. True or false? Arena has a built-in input analyzer tool that allows for the fitting of certain distributions of data. That is also true. It's a pretty cool tool, and I will say that having a tool that allows you to fit distributions to data is a very common feature among any kind of simulation programs or any kind of statistic programs. But Arena also has it as well. Question 6. Suppose that you have a continuous random variable x with PDF f of x equals 2x for and x can be between 0 and 1. So we want to find the inverse of x's CDF and then show how to generate the random variable x from a uniform 0-1 pseudo-random number. So what this question is really asking is, hey, we have this random variable x with some PDF, like given a uniform 0-1 random variable, how can we generate this variable x? So at the end of this question, we're going to have basically x equaling some function of u, and that's going to be our answer. And what we're trying to do is to find what is the function of u. Is that like what transformation do we need to do to our uniform random variable so that we generate x? So of course, the way you go about these kinds of problems, and this problem actually sort of tells you how to do it, is you find the inverse of x's CDF, and then what we'll do, and basically use that. So first of all, what is the CDF? So step one, what is CDF of x? So we have the PDF f of x, but to get the CDF we have to integrate it. So f of x, we basically integrate the PDF f of x. This is the PDF, and we integrate it from 0 to well, basically we want to integrate it from ideally, let me rewrite this. You really want to integrate it from like negative infinity to whatever value of x we have. However, because the PDF is 0, and it's like if we look at the limits of where x can be, x can at smallest be a value of 0. So our bottom limit can be 0, and we still do to x, so that way we end up with a function of x. And so this is f of x dx. And what is f of x? Well, that's our PDF, which is 2x, so that's just pulling in this guy here. And of course, then we integrate that. So, that ends up being x squared, and you evaluate it from 0 to this x value. So that ends up being x squared. So our CDF of x is just x squared. So that's the first step. The second step, recall that we have the inverse transform theorem that says that f of x, which is, or big X, is equal to a uniform random variable from 0 to 1. And so what we can do, put another way, because we have, this basically says that because we calculated what f of x is, which is equal to x squared, this says that x squared is equal to u. And this is just taking this value here that we calculated and plugging it in. And finally, step 3, we solve for x, and in this case, that's just taking the square root of both sides, so x is equal to square root of u. One thing that that is important to note here is that we're able to solve for x in this nice fashion because x can only be positive. It's between 0 and 1, and so taking the positive square root is okay in this case. If x could be negative, then we would have had to tread a little bit more carefully in this process and possibly take both the positive and the negative square root in some fashion. But in this case, because x can only be positive, because x is between 0 and 1, then this is okay. And so this is our answer. This is how we generate basically an instance of this random variable from a uniform random variable. Cool. Let's move on. So question 7. Suppose that you have two uniform random variables between 0 and 1, and you have two realizations of them. So you have a u1 equaling 0.45 and a u2 equaling 0.45. And they want us to use the Box-Mueller approach to generate two IID normal 0-1 realizations. So recall that, let me find this on my equation sheet. Recall that given that the Box-Mueller approach has an equation that looks like this. So -2 natural log of u1 times cosine of 2 pi u2, and there's another one which uses the sign u1 times sine of 2 pi u2. And the big idea here is that basically both these are given two of these uniform random variables. You can create two standard normal, which are this is z1 and z2. So these are normal 0, 1 realizations. And what you just have to do is you just have to plug in u1 and u2 into these equations, and you get your two normal 0, 1 realizations. So this is pretty standard. So if you plug it in, I could take out my calculator, but it's very on an exam I obviously would. In this case, it's just I'm just using the values given by the solution. But 3905. So it's pretty straightforward. You take this u1, you put it there and there, and you take this u2 and you put it there and there. Yeah, and you get your two realizations. So there's your answer. All right. Question 8. So suppose that you have z1, z2, and z3, and they're all IID normal 0, 1 random variables, so standard normal random variables. And let's define a new random variable t, which is equal to z1 divided by square root of z2 squared plus z3 squared divided by 2. We want to find the value of x such that the probability that t, which is our new random variable that we've defined, less than x, which is what we're trying to find, is equal to 0.99. So when you get a question like this, I know when I was taking this class, this question initially stumped me because I saw this kind of nasty expression and was like, oh my gosh, I have no idea how I'm going to find the probability of this. But one thing I will say, and this is a pattern in this class, is the way I would approach this is ask yourself, is this section that's in this blue rectangle, is that a fancy way of writing a simpler random variable? And this is something, that happens, I would say, on Dr. Goldsman's exams in another area as well. So, sort of like as a tangent. Tangent up here. How, he'll have a question, something like, let u1, u2, u3 be uniform 0, 1, and then he'll say let x equal, let's say, like 1 over 5 times times natural log of u1, and then 1 minus u2, and then maybe like u3, all within this natural log. And then he'll say something like, find the probability that x is like less than or equal to some value, maybe like 3 or something, and he'll be like, what is that? And in this is a very similar sort of question where you would have to recognize that, oh yeah, this thing is like an Erlang random variable, and then you would use the CDF of the Erlang to figure out what the probability is. So this is sort of like another related type of question. And so these kinds of questions happen a fair amount, where he'll give you something that is not obvious at first blush what is going on, but then once upon sort of further inspection, you can sort of simplify it to a random variable that you do know what's going on, and then you can sort of get your answer in a straightforward fashion. And so in this question 8, this is the same thing. This is really just the same thing. And so, it turns out, if you go through your class notes, one of the things that we have is that if z is a normal 0, 1 random variable, and y is chi-squared with n degrees of freedom, then the random variable z divided by square root of y divided by n is distributed as a student's t distribution with n degrees of freedom. So this is the student's t distribution. So that this is sort of a fact. And another sort of relevant fact is that if you take the sum of, let's say, you take the sum of n random variables where, let's say, each zi is an IID normal 0, 1 random variable in here. And so the sum of, n of these, we're summing up n of these, is a chi-squared random variable with n degrees of freedom. So in this case, one thing that you should sort of maybe start to notice here is that this definition looks pretty similar to this one, except not quite, because the bottom has standard normal z2 and z3 squared, but we want to have a chi-squared to meet this definition here. But, it turns out, of course, that z2 squared plus z3 squared, and this is just, using this formula, so we're just using that formula. This is distributed as a chi-squared of 2, and so therefore t, we're going to rewrite this here. We can rewrite this as a z1 divided by square root of chi-squared of 2, and then we still have that 2 divided by 2 in here. And now we satisfy sort of this form here. And so at this point, this is the same thing as saying t of 2. So student's t distribution with 2 degrees of freedom. And so what we want to do is we want to find the probability that a student's t distribution less than x is equal to 0.99. And if you look at this, this is sort of another way of saying, like, this is basically saying, like, hey, we want let's say f of x be the CDF of the t distribution, and we want to find x such that f of x is equal to 0.99. So put another way, we want to basically, in other words, find the inverse, basically, the inverse of 0.99, the inverse of the CDF, and that's sort of your answer. And so how do we go about doing that? Well, this is where we sort of use our nice standard, our nice tables. So if we go to these tables, which are provided with each exam, you can see the one we're interested in is the student's t-distribution table, which is this one here. And recall that our student's t-distribution has 2 degrees of freedom, right? Because it's a t of 2. And we want to find the values, basically the inverse, where you only have where things are less than 0.99. And so to have things less than 0.99, you basically look at the 0.01 table column, and then you look at this value here, and that is basically the value that we want. So 6.965. So going back here, so that means this is 6.965. And that is our answer. That is what x is. That is what the x that we were looking for, all the way over here. Let me draw a line. So this guy this is the x that we were looking for. So that is our answer. And I will say this is a bit of a trickier question, I think, than that. This is probably on the harder end of the spectrum, but if you can sort of go through this and are comfortable with all the pieces of this problem, I think that's, I would recommend you get to a place where that is the case. Okay, question 9. Suppose x has the Laplace distribution with PDF f of x equaling lambda over 2 e to the minus lambda times absolute value of x for x on the whole real line, and lambda is greater than 0. So this looks like 2 exponentials symmetric on both sides of the y-axis. So, if we were sort of to draw it, remember one exponential looks something like that, but this is sort of like, imagine it's symmetric, so it looks something like that. So that's probably what this PDF looks like. And we want to know which of the methods below would be very reasonable to use to generate realizations from this distribution. So first answer choice is ask a UGA student. That will almost never be the correct answer. Second, Box-Mueller. So Box-Mueller, this is used only for basically normal random variables, for generating normal random variables. The inverse transform method. So I think, the inverse transform method works but anyway, sorry, before I move on to inverse transform method. So Box-Mueller is only used for generating normal random variables, and this is a Laplace distribution, which is not a normal random variable. So that's not the answer. That's also not an answer choice. C, inverse transform method. So in order to use this one, you have to be able to get the CDF in a nice, easy, closed form. In particular, so you can, and just getting the CDF, not only do you have to get it in a closed form, but you have to then be able to take the inverse of it, also in closed form. And in this case, that is actually very doable. It's, you can imagine, it's the way, for the purposes of this class, the inverse transform method is not going to be usable for the normal random variables. So inverse transform method does not work for normal random variables, but it does work for a lot of other things. And unless the PDF is something pretty crazy and large that is not easily integratable to a CDF, then the inverse transform method will most likely work. So, this I think is a valid way. But in this problem, there's also an answer choice that lets you pick 2 of them, so let's keep going. answer choice D is acceptance rejection. So acceptance rejection is, when you basically it's a method of it's like, how do I explain it best? Acceptance rejection is a way of like doing things of like picking values. Let me explain. Sorry, I had a brain fart there. Acceptance rejection is a way of generating realizations from a distribution if the PDF is, particularly complicated. You can also use acceptance rejection even if the PDF is pretty simple, and that works great as well. But it is definitely more widely used if the PDF is very, very complicated. In this case, the PDF is not very, very complicated, so that doesn't really affect us. But regardless, acceptance rejection is sort of a good method in general for a lot of random variables. So in this case, the answer choice is F because both C and D are true. One other thing I'll point out for acceptance rejection is that you need to have the PDF be finite in order to really use it accurately. And in this case, that is also the case because this thing will always sort of be a finite PDF. All right. Question 10. Consider a bivariate normal distribution, I guess random variable pair x, y, for which the expected value of x is -3, the variance is 4, the expected value of y is -2, and the variance of y is 9, the covariance of x, y is 2, and we want to find the Cholesky matrix associated with xi, i.e. the lower triangular matrix C, such that if you take the C and multiply it by a C transpose, you get sigma, which is the variance. Sigma is the variance covariance matrix. So in this problem, recall that you have, and this is something you should probably have, of course, on your cheat sheet by now, the Cholesky matrix. We have this nice way of getting it, so let me just write that out. Sigma 1, 2, square root of sigma 1, 1, and then 0, and then square root of sigma 2, 2, minus sigma 1, 2 squared, divided by sigma 1, 1. So this is this is how we go about computing it. We just have to plug in sigma 1, 1, sigma 1, 2, and sigma 2, 2. So, but what exactly are those? So what is sigma 1, 1? So this is just basically, you can think of that as the variance of x. What is variance of x. Let me think for a second. And then sigma 1, 2, that's the covariance between the two, which is, so the variance of x from our definition is 4, the covariance in our case is 2, sigma 2, 2 is the variance of y, which is 9. And these are all just coming from up here. So variance of x is 4, variance of y is 9, and covariance of x, y is equal to 2. And so at this point, it's just a matter of plugging in these numbers into this matrix. So let's go ahead and do that. So here's our matrix. Sigma 1, 1 is variance of x, so that's square root of 4. This is still 0. Sigma 1, 2 is 2. And then divide by square root of 1, 1, which is square root of 4. And then this other guy over here, sigma 2, 2, is 9. And then minus sigma 1, 2 squared, which is 2 squared, divided by sigma 1, 1, which is 4. And so if you sort of rewrite this, this is 2. This next one here is going to be 1. After you simplify that, this is still 0. And the last one, 9 minus 4 over 4 is just 8. So that's square root of 8. I believe Dr. Goldsman, he simplifies it. So square root of 8, of course, is equal to square root of 2 times 4 in there. And that is equal to square root of 2 times square root of 4, which is equal to square root of 2 times 2. And if you rewrite that, that's 2 square root of 2. And so, the fancy way of saying 2, 0, 1, and then 2 square root of 2. And that's the answer that Dr. Goldsman has in the test. And so that's our answer for that one. It's really a straightforward problem. Moving on. Question 11. Consider a non-homogeneous Poisson arrival process with rate function lambda of t equaling to 2t. So for t greater than or equal to 0. So in this case, we want to find the probability that there will be exactly 2 arrivals between times t equals 1 and t equals 2. So how do we go about doing this? Well, what you first want to do is we basically want to the number of arrivals. So number of arrivals between t equals 2 and t equals 1. So this is number of arrivals between times t equals 1 and t equals 2. This is distributed as a Poisson distribution with lambda equaling basically you integrate the lambda of t function from t equals 1 to 2. So dt, like that. So let's sort of like take this for a second. And so what exactly is this 1 to 2 lambda of t dt? Well, we just plug in this 2t into here. So this is the same thing as saying 1 to 2, 2t dt. And that ends up being t squared and evaluated from 1 to 2, which ends up being 4 minus 1, which ends up being 3. So that basically is saying that this thing is the same thing as saying a Poisson of lambda equal 3. So what we're saying is that in plain English, or as close to plain English as we're going to get in this class, the number of arrivals between times t equals 1 and t equals 2 is distributed as a Poisson random variable with lambda equaling 3. And so in this question, we want to find the probability that there will be exactly 2 arrivals. So in this, so in this problem, and I'll sort of like talk about variations on this problem, but in this problem, we want to find the probability that there are exactly 2 arrivals. So anytime you have a distribution and you want to find the probability that something happens that the random variable takes on an exact value. If it's a discrete distribution like the Poisson is a discrete distribution, then you want to take the PMF of this. So recall that the PMF of Poisson is f of x equals equals e to the negative lambda times, I erased something, e to the negative lambda times lambda to the power of x divided by x factorial. And so at this point, we just plug in things. So we know that lambda is equal to 3. And what is x? Well, x is 2, because we want to find the probability that there are exactly 2 arrivals. So we want to basically find, f of 2, and that'll tell us the probability of these things. So if you plug in the numbers, so you have e to the minus, so lambda is, remember, 3, because that's what we calculated earlier. So minus 3 times 3 to the power of x, which is 2, and divided by x factorial, which is 2 factorial, which is just 2. So this ends up being, you have 9 halves times e to the minus 3. And if you actually go and sort of like plug this into a calculator, you will get something close to 0.224, whatever it might be. And so that is your answer choice C, and that's how you do that problem. One thing I will point out is that there is a variant of this problem. So a variant would be, something like find the probability that there will be at most 2 arrivals between times t equals 1 and 2. And how do you go about solving this? So basically, everything is same except at the end, use the CDF instead of the PMF. Right? Because in this case, we want to use the CDF to find the probability that x is at most some value, which is a fancy way of saying x is less than or equal to that value. So, and of course, another variant could be, what's the probability that x is at least, that the number of arrivals between times t equals 1 and 2, that number is at least 2. And so in that case, you'd also use the CDF, but of course you'd take 1 minus the CDF in that case. So yeah, just wanted to sort of like give you guys some of the variants and show you how to approach this problem. All right, moving on. Question 12. Suppose we are generating arrivals from a non-homogeneous Poisson process with rate function lambda of t equals 1 plus sine of pi t, so that the maximum rate is lambda star equal 2, which is periodically achieved. Suppose that we generate a potential arrival at time t equals 0.75. What is the probability that our usual thinning algorithm will actually accept that potential arrival as an actual arrival? So in this case, this is using the acceptance rejection method. And basically what you do is you take lambda of t equals 0.75, and you divide that by lambda star. So that's with our probability. So our probability is equal to that. And so what is lambda in the denominator? Lambda star is just equal to 2. That just comes over here. And then the numerator, we have 1 plus sine of pi times t, which t is equal to 0.75. Make sure to do this calculation in radians. So, this is a guy, that's just this equation here. And I just plugged in the t equals 0.75. And when you go through and sort of run the numbers here, you end up getting 0.854. And that's your answer. So there's that. All right, moving on. Question 13. Suppose x1, x2, ... is an IID sequence of random variables with mean mu and variance sigma squared. So consider the process, and it's a lot of sort of like text. What is the asymptotic probability that yn of 4 will be at least 2 as n becomes large? And so this one is definitely a little bit intimidating of a problem at first, because it the intimidating thing really is sort of this guy here. But the key here is that, and they actually give you the hint here in the problem. They say, recall that Donskoy's theorem states that ynt converges to a standard Brownian motion as n becomes large. So what this is a fancy way of saying that basically this whole thing, the y of n of t, it converges basically to standard Brownian motion, like w of t, as n goes to infinity. And that's sort of a, let's see, how should I put it? Mean view. The way we can go about, by the way, just to like put this piece by piece. So the way we sort of got here is I equals 1 and nt, and you have xi minus mu divided by sigma square root of n. And the key here is that each of these random variables have mean mu and variance sigma squared. So what happens to an xi? So if you have an xi and you subtract the mean and you divide by the the square root of the variance, which is just sigma, then that's basically just a way of saying a standard random normal variable. So that's still I equals 1 nt. And so this is, you basically let, I don't know, zi be a basically a standard normal random variable. And recall that standard normal means that it's a normal random variable with mean 0 and variance 1. So this is a fancy way of saying that here we have z of I, and we still have to divide it by the square root of n. And then of course we can sort of move that square root of n out in front, and you have I equals 1 and still this nt business, and you have z of I. And at this point, one of the lecture slides, which I would recommend, sort of, it has a lot of like in the whole Brownian motion part of the class, one of the lecture slides mentioned here that, let me rewrite this so it's more legible, that if you have this guy, this basically approaches the W of t distribution as n approaches infinity. And so that's basically the long way of how we got to here. And so also recall that another property is that the W of t distribution is the same thing as a normal random variable with mean 0 and variance of t. And so in this case, what you have is we basically are saying that we have this whole process. So we have yn of 4, which is the same thing as a w of 4, which is the same thing as a normal random variable with mean 0 and variance of 4. And we want to find the probability that this thing, basically that the normal 0, 4 will be at least 2, right? And so that's the way we go about doing that is and let me start using some space up here. So how do we find that? So we want to find the probability that a normal 0, 4 is greater than or equal to 2. Well, of course, what you can do, we can take we have probability, and on both sides of this inequality, we can take if we take 2, recall that you can convert the normal 0, 4 to a normal 0, 1 by subtracting the mean, which was 0, and divided by the square root of the variance, which is 4. And so, and this basically this is 0 comes from that guy, and this 4 comes here. And so now we have the probability that a normal 0, 1 random variable is greater than or equal to, if you simplify 2 minus 0, it's 2 divided by square root of 4, it's also 2, so then 2 divided by 2 is 1. So now we have the probability that a normal 0, 1 random variable is greater than or equal to 1. And at this point, you know, we've done a lot of stuff in this class like this, so it's really sort of the same old process where we will, you know, this is equal to 1 minus the probability that normal 0, 1 is less than or equal to 1. I guess if we were being strict, it's just like that. But it for continuous random variables, it won't make a difference. And what is this value? Well, let's look that up by looking in the normal tables. So that's basically, we want the probability that this is less than or equal to 1 is 0.8413. That comes from here. So going back to this one, so that's equal to 1 minus 0.8413, and that ends up being 0.1587, and that is our answer. So that's how you go about solving this problem. Cool. Question 14. Which one of the following properties of a Brownian motion process W of t is false? So is it W of 0 equals 0, W of t? Well, let's go through each one of these in turn. And so only one of these is going to be false, right? So first of all, W of 0 is equal to 0. That's definitely true. W of t is distributed as a normal 0, t random variable. that is also true. These are very fundamental things from, I think most of these are compiled on one of the slides that Dr. Goldman presented. But either case, I would recommend having all these properties written down on your cheat sheets. Next one, W of 3 minus W of 1 has the same distribution as W of 11 minus W of 9. And so that is also true, because that's basically another like theorem, and I would consult the slide for more information. And D, you have W of 3 minus W of 1 is independent of W of 4 minus W of 2. This one is actually not true, because the range 3 to 1, because 3 to 1 overlaps the range 4 to 2. If instead you said W of 3 minus W of 1 is independent of, let's say, W of 7 minus W of 5, this would be true, this statement, because the values are the ranges are not overlapping. But in this case, because you have 3, 1 overlapping the range between 4, and 2, those are overlapping, and so that's why this one's not true. And then finally, the last one, covariance of W of 3, W of 5 is equal to 3. This is true because you take the minimum. This is just another one of those fundamental properties. So that means the answer choice is D, because that's the one that's false. And I would recommend, I think I've already said this, but write this stuff down on your cheat sheets and sort of, it's pretty straightforward. You can almost guarantee there will be a question like this on the exam. So just get your points by having this, by understanding this, by having it written on your cheat sheet. Cool. Question 15. Find the sample variance of -10, 10, and 0. So in this case, how do we go about calculating the sample variance? Well, the definition of sample variance, S squared, is 1 over n minus 1, and then you take the sum of basically the random variables. You have xi, basically the data points, xi minus x bar, which is the sample mean. So this is the sample mean. And square that. So let's sort of like plug and chug. So what is n? Well, n is equal to 3. So n minus 1 is 2. And then the summation for this is we have x. So what is x bar? That's just basically the sample mean. And in this case, you can tell, it's -10 plus 10 plus 0 divided by 3, which just ends up happening 0. So that's really nice and convenient. So our sample mean is just 0 in this case. So we just have, -10 squared plus 10 squared plus 0 squared. And that ends up being, 1/2 times 100 plus 100, which ends up being 1/2 of 200, which is 100. And so that's our sample variance. So that's pretty straightforward. Yeah. So that's that one. Moving on. Question 16. If x1, x all the way up to x10, so you have 10 of these things, are IID exponential 1/7, i.e. having mean of 7, what is the expected value of the sample variance S squared? So recall that so there's the sample variance. So sample variance, which is S squared, recall that this is unbiased for the true variance, which is, let's call it sigma squared. And so that what this means, which basically is saying that the expected value of s squared is equal to sigma squared. And, this is sort of, interesting that this, but yeah, one thing I'll sort of just like briefly point out is make sure that you sort of understand the difference between the sample variance. So recall that the sample variance has a formula that goes something like n minus 1, and then you have like xi minus x bar and squared. And so that's the sample variance, and as opposed to the maximum likelihood estimator of the variance. So this is the MLE of variance, and this is, so this guy is the sample variance. And the only real difference between these two, because they have really the same formula, except the big difference is instead of it being 1 over n minus 1 on bottom, it's 1 over n. So this is the only difference between these two formulas. And anyway, but regardless, so in this case, the expected value of the sample variance is just equal to the true variance. And the true variance, of course, is, let's see, so we have the true variance of, what are we doing here? So we have 10 of these IID exponential random variables, and we want to find the true variance of them. And so that ends up being 1 over n times basically, let's see, one sec. The true variance, one sec, let me just erase this a little bit better and do this. Let me check my notes for a second. So the true variance is going to just be equal to the variance of, any one of these xi's. And what is the variance of the exponential distribution? So recall that, the variance of exponential, if you check the notes, exponential is 1 over lambda squared. And so that means this is 1 over lambda squared. And what is lambda? Well, we were told that lambda is equal to 1/7. That's what this guy here means. So 1 over 1/7 squared, and that ends up being 49. And so that's how we get our answer. Yeah. Moving on. Question 17. True or false? The mean squared error of an estimator is the square of the bias plus the square of its variance. So this is a pretty straightforward one. It's false. Why is it false? It's because the mean squared error definition of some estimator is equal to the let's see, basically the bias squared plus just the variance, but we don't actually square the variance. So the reason this is false is because we have this word square in it. All right, moving on. Question 18. If x1 is equal to 7, x2 equals 3, and x3 equals 5 are IID realizations from a normal mu sigma squared distribution, what is the value of the maximum likelihood estimate for the variance sigma squared? So this problem, very similar to a problem that I was talking about in problem 16, where it's very similar to problem 16, because we're just calculating, but instead of doing this 1 over n minus 1, we do 1 over n. So we use, that's the formula, so sigma hat squared, that's the maximum likelihood estimate for the variance sigma squared, that's equal to 1 over n times, basically we take xi minus x bar and square it. And so what is x bar? That's the sample mean. And what is the sample mean in this case? Well, you have 7 plus 3 plus 5 divided by 3, so that's equal to 5. So our sample mean is 5. What is n? N is equal to 3, of course, because we have 3 random variables. So this is 1 over 3 times, and then we have xi, which is 7, minus 5 squared, plus we have 3 minus 5 squared, plus 5 minus 5 squared. So that's just a 0, so that's easy. So we have 1/3, and then this first one is 2 squared, so that's 4, plus also negative 2 squared, which is also 4, so that's 8/3, which ends up being, so that's 8/3, and if you sort of divide that out, that ends up being like 2.67 or whatever, but that's our answer. Cool. Next question. Question 19. Suppose that we take 3 IID observations, x1 equals 2, x2 equals 3, and x3 equals 1 from we have a distribution that's exponential with lambda. Using the maximum likelihood estimate for lambda, find the maximum likelihood estimate of the probability of that x is greater than 2. So in this case, recall from class notes that the maximum likelihood estimate of lambda, which is lambda hat, is equal to 1 over x bar. And what is x bar? X bar is just the average of our observations. So this is 1 over, so x bar in this case is equal to 2 plus 3 plus 1 divided by 3, which is 2. So this is 1 over 2. So lambda hat is 1/2 basically. And then, you have this invariance property of maximum likelihood estimators, which says that if you have any function that involves a parameter, you can just, the maximum likelihood estimate of your new function can just use that maximum likelihood estimate of that parameter to sort of to get the things you want. So that's saying that, let's say that we have the probability that x is greater than 2, which is what we're interested in. And we want to find the maximum likelihood, which is put by this hat that I'm putting on it. So this is, the maximum likelihood of this. What we can do is we can sort of, this is the same thing as saying like, 1 minus the probability that x is less than or equal to 2 hat. So this is still the maximum likelihood estimate of that. I just switched sort of the way the inequality went. And then we can recall that this guy here is just the CDF of basically of exponential random variable. And so what is the CDF of the exponential random variable? Well, the CDF of the exponential random variable is equal to 1 minus e to the minus lambda x. And so if we sort of like plug this in, we have 1 minus e to the minus lambda x. So that's just, I just plug that in. And then sort of simplifying this math out, and of course we have to maintain the hat, but now the hat only goes on the lambda because we've, previously we had the whole probability expression, but now we can, the hat's only on the lambda. So simplifying this expression, we have 1 minus 1, which is 0, and then the minuses cancel out, so you have e to the minus lambda hat x. And then you plug in, we plug in our value for lambda hat that we calculated into here. So we have e to the minus 1/2, and what is x, well, x is, in this case, was 2. That's coming from this guy. X. Yeah. There we go. So that goes there. And when you, and that's equal to e to the minus 1. And if you do that math, it's 0.368. Right? Cool. Next question. Question 20. Suppose we're conducting a chi-squared goodness of fit test to determine whether or not 100 IAD observations are from a Johnson distribution with S equals 4 unknown parameters A, B, C, and D. And if we divide the observations into k equals 10 equal probability intervals, and we observe a goodness of fit statistic of chi-squared naught of 14.2, will we accept or reject the null hypothesis of the Johnson? Use the significance level alpha equals 0.05 for your test. So in this case, they tell us what the statistic is. We just need to sort of find the critical value. So how do we find the critical value? We will need, we have most of the information, but one thing we'll need is we'll need to find the degrees of freedom. So the degrees of freedom, which is V, is equal to k minus S minus 1. And so k is the number of buckets that we have, so that's this guy. S is the number of unknown parameters that we have, so that's this guy, number of parameters, so that's 10 minus 4 minus 1, which is equal to 5. And next, we have our level of significance, alpha equals 0.05. So at this point, we go to our table. So keep in mind 5 and 0.05. So we go to our table, and we want to go to the bottom one, which is the chi-squared table. And we look at our degrees of freedom, which is 5. And we want to, basically, our significance level is 0.05, right? And so that is 11.0. So that's, I just basically found this value. So it's 11.07. So taking that value, so that means our critical value is 11.07. And so we ask, is basically chi naught squared greater than our critical value of 11.07? What is chi naught squared? Well, that's 14.2, and it is, so yes, and therefore we reject. We reject the null hypothesis, and that's our answer. All right, moving on. Actually, before I move on, one other thing I'll say about this one. Make sure that you are able to actually calculate the statistic. I mean, in this case, they gave you the pre-calculated goodness of fit statistic of 14.2, but definitely also know how to calculate this value yourself given some data if you need to. Okay? All right, moving on. Question 21, true or false? The Kolmogorov-Smirnov test can be used both to see if, 1, data seem to fit to a particular hypothesized distribution, and 2, if the data are independent. So this is false because the KS test is only used to determine goodness of fit, so the first one, so this guy, true, but 2 is false. It's not an independence test at all. So that's a pretty straightforward one. Also, I'd be just be familiar with the various tests that we used for independence and goodness of fit. For independence, we used tests such as the runs test above and below the mean, runs test up and down, be familiar with the various tests and how to apply them, because there's a chance you might have to do that on the exam. So, all right, moving on. Question 22. Let's run a simulation whose output is a sequence of consecutive customer waiting times in a crowded store. Which of the following statements is true? A, the waiting times are independent. B, the waiting times are correlated. C, the waiting times are normally distributed. D, the waiting times are identically distributed throughout the day. So, basically, they're not going to be independent, right? Because if somebody's standing in front of you in line and they're waiting in line, it's going to affect how long you're waiting in line as well. So they're not independent. Are they correlated? Yeah, I would say they probably are correlated. Are they normally distributed? Probably not. It's probably there's probably times when there's very low waiting times and there's times when it's very high waiting times, but there's probably not a ton of stuff in the middle. In either case, it's probably not normally distributed. And D, the waiting times are identically distributed throughout the day. That's also not true. You can just go by your intuition. There's definitely times when the people will be waiting more, or it's not going to be like if you go, to a let's say you go to the mall at like 1 p.m. on a Wednesday, it's going to be a lot less crowded than if you go to the mall at like 1 p.m. on a Saturday, or like various times of day. So throughout the day or even in between days, it will vary. But yeah, even within the same day, like, you can imagine that at 1 p.m., lots of people are at school or at work and so aren't at the mall, versus at like 5 or 6 p.m., they've got off work, they got off school, maybe they're going to go hang out with their friends. So it's, they're definitely not identically distributed. Cool. Question 23. Suppose we want to estimate the expected average waiting time in minutes for the first m equals 100 customers at a bank. We make r equals 3 independent replications of the system, each initialized empty and idle and consisting of 100 waiting times. The resulting replicate means are, and they give them to you here in this table. Find a 95% two-sided confidence interval for the mean average waiting time for the first 100 customers. So recall for this one that we have a 90%, so we want to, let's see, we have this formula. So the mean mu, which is the average waiting time, it's in the value zr bar plus minus t alpha over 2, r minus 1, and square root of sz squared and divided by r. And so we just need to sort of like plug in the pieces here. Also, one thing I would point out is I would recommend that you are familiar with, there's a lot of problems that are similar to this one, where they give you independent replications, or maybe they give you a bunch of batched means, or maybe they do something else, and they want you to find the confidence interval or like find something else out about it. And it's important that you can write these formulas down on your cheat sheet, but I would recommend being fairly familiar about which formula to use when, and just being very familiar with what all of the different symbols mean, so that way when you get on a test, you're not like, you don't sort of freeze up and not know which one to use and just get confused. So in this case, of course, what is z of r? Z of r, and let me check my notes for my formulas here, because I do not have all these things memorized either. But thankfully that is why I have cheat sheets. So the z of r bar is equal to 1 over r times I equals the sum of all the zi's. So it's basically the average of the zi values. So this is 12 plus 14 plus 11 divided by 3, and that ends up being 12.333. And then what is t alpha over 2 r minus 1? Well, alpha in our case is 0.05, so this is, and dividing it by 2 is 0.025. And then r is equal to 3, but r minus 1 is equal to 2. So that's that. And if you look this up in your standard normal table, so let's look that up. So 0.025 and 2. So we have to go up here. Let me erase my old marks. Okay, 0.025 and 2. So we have 2 degrees of freedom, and we want 0.025, which is right this column here. And so the value we have is 4.303. So we grab that, which is 4.303. And finally, what about SZ squared? How do we get SZ squared? Well, SZ squared is equal to 1 over r minus 1, and then I equals 1 to r, and it's zi minus zr bar squared. And so we calculated what zr bar is. That's this guy here. We know what our r value is. And so at this point, it's just a matter of sort of plugging in the numbers and doing the math. And if you do the math, I think you get something like 2.333. And finally, what we do is we plug in all of these values. So, we plug in this value of SC squared into here. We have our value of r. So we have SC squared, we have r, we have this guy, and we have this guy. And when you do all the values, you'll find that mu is in the range of 8.538 and 16.128. And so that's how you go about getting this. All right, moving on. Question 24. Suppose that you have a 90% confidence interval for the mean, and suppose that this interval was based on 4 independent replications of the underlying inventory system. Unfortunately, the boss has decided that she wants a 95% confidence interval. Can you supply it? So what we recall that how we got this confidence interval. So we had let's say -30, 90. The way we got here, you had x bar plus minus t alpha over 2, and then basically like b minus 1, and time, let's see, one sec. Times basically y, which, give me a second, let me think for a second. Yeah, so basically this confidence interval has x bar plus minus t of alpha over 2 b minus 1 times basically some other stuff. So we'll call this some other stuff that we don't need to necessarily care about that much. It's stuff like, I think, basically the variance and other stuff. And the big point here is that we want to figure out, we want to modify the confidence interval. So how do we go about doing this? Well, first of all, we want to find out what x bar is. And x bar is always just going to be halfway between the two ranges. So negative 30 plus 90, x bar is going to be equal to 30, because that's, halfway between negative 30 and 90. So there's that. And so that tells us that basically this t alpha over 2 comma b minus 1 times stuff, which, like I said, it's like the variance and stuff, this thing has to equal 60, because you take 30 plus 60 and you'll get your 90, and you take 30 minus 60 and you'll get negative 30. So that's where we're at here. We have this 60 value. And what we'll want to do is let's grab, recall that in this case, t alpha over 2, in this case, the alpha that we used here was a 0.05, and b minus 1 in this case was 3. And this is 0.05 because we have a 90% confidence interval. So that's how we get alpha equaling 0.1, and then it's alpha over 2, so it's 0.05. And so we have this, but we want to, one thing we can do is we can find what this stuff is. So stuff is equal to 60 divided by basically t 0.05 comma 3. But we don't really care about that. But what we do care about is if we multiply stuff by the actual t value that we want, which is a 95% confidence interval. So that's a 0.025 comma 3. If we multiply it by that, and if we do, x bar plus minus that, that'll be our answer. And so another way of writing this, of course, we know what our x bar is, which is 30, because we calculated that earlier. We know what our stuff is. Our stuff is this 60 over t 0.05 comma 3 times, and then we multiply it by this value, 0.025 comma 3. And if you look up these values, you get 30 plus minus 60 times, I believe, it's 3.182, and then divided by 2.353. And once you sort of do the math, you will get negative 51.14 and 111.14, and that's your new confidence interval. So that's how you go about doing this problem, basically. Yeah. Cool. Question 25. True or false? Welch's method is a graphical technique to estimate truncation initialization bias points for steady-state simulation. This is very true. And recall that Welch's method, imagine that you have a simulation, and so this is our t-axis, and here's our, whatever values. Recall that as the simulation starts up, it might take a while to get up to its steady state, and then eventually it'll actually be in its steady state. So Welch's method is just hey, can we sort of graphically look at a chart and find this point, and then only take the data, after that point, so we don't have any of this initial garbage. So that's 25 is true. Question 26. Suppose that we're studying a stochastic process whose covariance function is rk equals 3 minus k for k equals 0, plus minus 1 plus 92, and 0 otherwise. Find the variance of x3, the sample mean of the first 3 observations. So this is definitely I guess, more involved question that uses some more, I'd say, specific obscure knowledge in the class, I would recommend having the formulas written down. So the formula is something like, var x n a bar is equal to 1 over n, and then you have r naught plus 2 times sigma k equals 1, n minus 1, and in here you have 1 minus k over n, rk. And so that's your variance, and then what you do is you plug in all your basically rk we have equaling 3 minus k, so you plug that in here. We have k equaling a couple different values. So what is r0? R0, of course, in our case, so r0, recall, is equal to 3 minus k, which is 3 minus 0, which is 3. So this guy is 3. N, n of course is 3 because we're finding the variance of x3, so n is equal to 3, because that's how many 3 observations. We know what, and then we have this sum, and we know what n is in this sum. That's equal to 3, and so at that point, this n is also still equal to 3, and really we just do this. You just sort of do the math, and at the end you get something like 2.111, and that's your answer. Yeah, this is pretty specific. I would recommend just having, this equation here on your cheat sheet and understanding how to use it, and that way if this problem appears on a test, you're ready to go and you can go and solve it. Question 27. Consider the following 5 observations. So you have 54, 80, 75, 62, 90. If we choose a batch size of 3, calculate all of the overlapping batch means for me. So basically, we want to find the first batch mean is going to be the mean of those. Second batch mean is going to be the mean of these, and the third batch mean is going to be the mean of these 3 guys. And so you just calculate the mean of these 3 things, and I believe, if you do it, you get like 69.7, 69.7, and you get 72.3, and you get 75.7. So you just take the average, right? So like for this first one, it's 54 plus 80 plus 75 divided by 3. And then these ones are similar. This one is like, 80 plus 75 plus 62 divided by 3. And this last guy is the same thing. Cool. Moving on. Question 28. Which variance reduction method uses the difference x bar minus y bar of 2 positively correlated sample means to get a lower variance estimator for the difference mu x minus mu y of the underlying unknown means? So in this case, if you have positive correlation of these things, that's going to be using common random numbers. If you have negative correlation is this guy, negative correlation. You would use antithetic random numbers. And composition doesn't really even make sense in this context. But stratified sampling that can be used, but not in this not in this context. Cool. Moving on. So question 29: which variance reduction method most closely resembles regression? Example, basically of the form, like y equals x bar minus this, where you have a constant and blah blah blah. Anyway, anytime you hear the word regression with regards to variance reduction, where you're doing some kind of like line fitting or that kind of stuff, that is the control variance method. So that's just some good knowledge that you hopefully, if this is confusing to you, rewatch the slides on variance reduction that talk about common random numbers, antithetic numbers, control variates, and that stuff. You don't need to have as long as you understand the fundamental concepts, I think you'll be in a good place. Question 30. If you are using a ranking and selection procedure and two competitors happen to fall within the indifference zone, then you really don't care too much about which one you end up selecting. Yes, so this is true. That's the definition of the indifference zone, is that if they fall within the same zone, then you don't really care which one you end up selecting, because that is how you sort of defined the problem. So moving on. Question 31. Suppose we are interested in determining which of 3 soft drinks is most likely to be chosen by a person in a survey. Which type of ranking and selection problem is this? So in the case that you're trying to determine which one of like multiple things is the best, that is the multinomial. And that's just another factoid. Cool. Question 32. True or false? Sequential rank... Oh, whoops. Yeah. Let me say that one more time. Question 32. True or false? Sequential ranking and selection procedures are designed to stop early if one alternative seems to be way out in front of the others. This is also true. And there could be a problem similar to one of the problems in the homeworks where they might ask you this question in another form. They might say something like, they might actually give you numbers and, tell you what is the like n star number of samples that you need and all that stuff, and then ask you like, hey, should we stop early or should we keep going? So this question could be asked in a number of different forms. So just sort of be expecting that. Cool. Question 33. Suppose when designing a ranking and selection procedure, you have decided to increase the desired probability of correct selection compared to a previous run of this procedure. What can you expect? And so if you want to increase the desired probability of correct selection, you'll obviously have to pay a price for that. And so the price that you have to pay is that you need to collect more data. And so larger sample sizes is the answer. All right, moving on. Finally, zombies or Bieber. Dr. Goldsman has a great sense of humor. I will say probably like 99.9% of the time, the answer to these kinds of questions is the non-Bieber option, so the zombies. Yeah. All right, cool. So that's the end of this review session. Yeah, thank you guys for listening in, and good luck on the test.